we are going to find a vector that is orthogonal to both the given vector u and v. So in general, we take advantage of the properties of the cross product. So I try to draw 3 dimensions here. Let's say we have the vector u and the vector v on a plane. When we do the cross product of u and v, we're going to have a vector that is orthogonal to the plane containing u and v. And this will obey the right hand rule. So if we have the first vector, this one, the second vector doesn't have to be orthogonal. It could be anywhere, like this. When we do the cross product of these two vectors, we're going to have to have, it's going to be the third vector that is orthogonal to the plane that containing those two vectors, which is the paper here. So the cross product is going to give us this vector. Right. So again, the right hand rule. The index finger point in the direction of the first vector. The second finger on the direction of the second vector. So the index and the third finger, and the thumb is going to be the direction of the cross product. Again, it doesn't have to be orthogonal. It could be wherever the second vector is, and the thumb will point into the direction which is pointing up, the direction of the cross product. Right, that is the right hand rule. So first is the index, the second vector is the third finger, and then the thumb is the product, the cross product. Right, now that we have it, we can go back to zoom back into our problem. Right, so pretty much all we do is just find the cross product of u and v here, and that's pretty simple. U cross v, the vector u has 3 components of 3, -1, and 2. Cross with the vector v has 3 components of -2, 2, and 4. And that is a 3x3 determinant of 3, -1, and 2, -2, 2, and 4. Right. And we did fly with that before, so we have to that. Go over I, go over J, and K. So just have -1 and 2, 2 and 4 for I, and then 3 and 2, -2 and 4 for J, and 3 and -1, -2 and 2 for K. Right, and that gives us once again 2x2 determinant. We're going to take this product minus this product, so -4 minus 4, so -8 in the I direction. 3 and 4, that will be 12, minus -4 is +4, so 12 plus 4 is 16, but we have the minus, have the opposite sign, so it's going to be -16J, and then 6 minus 2 is going to be 4K. And so this is the vector that is orthogonal to both. By the way, it is the right hand rule again. Let me just zoom out last time. So it's the right hand rule. First, second, and the product is going to be pointing up. Now if we turn it around, the first vector and then the second vector, it could be pointing down into the paper. and that vector is also orthogonal to those two. So this is u cross v. In theory, we can also find the vector that is orthogonal to both pointing down, in which case this is going to be v cross u. So if we take v cross u, we're going to have a vector that is opposite to this. It is opposite to this, but it is still orthogonal to u and v. So we can take u cross v or v cross u. Either way, we should have a vector that is orthogonal to the plane containing the vector u and v, either pointing up or pointing down, with respect to the plane, of course. Now let's zoom back in, and that's what we have for this problem.